Hi everyone. So let's go ahead and take a look at section 6 of, that's weird, that should be chapter 23. I'm not sure why it says 26. But anyway, so what we're doing is we're continuing on this whole process of respiration. So remember there's 4 processes of respiration. There is pulmonary ventilation, there's alveolar gas exchange, and then there's gas transport, and then there's systemic gas exchange. So the last thing that we talked about was that huge process of pulmonary ventilation. So now we're going to be taking a look at we're going to take a look at the second and the last step. We're just going to go ahead and get the last one out of the way with alveolar gas exchange, because it's really going to be the same concept. So that's why we're going to look at both of those here at the same time, even though there's a step in between. Just remember that. So remember that alveolar gas exchange is going to be when gases are being exchanged from the alveoli and the pulmonary capillaries. So depending on if it's oxygen, it's moving from the alveoli into the bloodstream, or if it's carbon dioxide, it's moving the opposite way, from the bloodstream into the alveoli. Remember, systemic gas exchange is going to be what's happening once that blood transports the gases. What is happening, or specifically oxygen. If we're looking at oxygen, we're going to take a look at systemic gas exchange and what happens to oxygen once it gets to the cells and how it moves from the bloodstream into the systemic cells, but also how carbon dioxide moves from those cells into the bloodstream. So that's what we're going to be looking at. Before we do that, let's take a look at some chemical principles of gas exchange. So now we have even more gas laws. Yay! So if you didn't like that chemistry before with Boyle's law, you're not going to like it here either. We've looked at this before. Very briefly, I talked about this, but remember earlier in some other slides and other sections, you saw that P in front of like the O2 or CO2 and then the O2. That P represents something called partial pressure. And partial pressure is going to be the pressure exerted by each gas within a mixture of gases. So we'll talk about how important these partial pressures are, because each gas independently is going to move down its own partial pressure gradient for gas exchange. So when we were looking at ventilation, all the gases were just moving in, right, from a high pressure to a low pressure. Now we're getting to where it's each individual one. We're going to be taking a look at how there's going to be a little bit of oxygen in the atmosphere, and then there's going to be a little bit of oxygen in the pulmonary air, and how it's going to give rise to this partial pressure. And we have to take a look at the pressure that's going to be the partial pressure in the blood as well. So that brings us to Dalton's law here in a second. The fact that atmospheric pressure is 760 millimeters of mercury at sea level. So that means that if we added up all of the major gases in the environment, it should equal up to 760. So we're going to add up all of the nitrogens, because there's a certain percentage of nitrogen in the air, and if we take that percent, it should add up to equal up to 700, or with all of these, it's going to equal up to 760. We're going to go in and take the partial pressure of oxygen as well, carbon dioxide, and H2O. These are the main ones that we're going to look at. There are other minor gases in the environment, but these are the main ones that are going to go in and contribute to this 760 millimeters of mercury. Let's see how we calculate that, because we love math. I love math, so I know some people don't like math. But so nitrogen is going to be the most abundant gas found in the air. There's actually 78.6% of the gas in the air is nitrogen. So in order to find out the partial pressure, we have to go in and take that 78.6%, and multiply it by 760, and that will give you your partial pressure, 597. So if we know the percentage of all of the other gases, we should be able to go in and calculate the partial pressure of all of the other ones. And when we add them all up, it should equal 760. Let's see if it does that. There's Dalton's law. It means that when you add up all of the partial pressures, it should sum to the total pressure. And this one is just looking at the atmosphere, the gas around us. We'll take a look at how it actually changes once we get into the alveoli. So look, there's that 597 millimeters of mercury because of the percentage. I don't expect you to know how to calculate these. If you love math, then you go for it and calculate them. But you don't have to worry about knowing how to do this for your exam. And of course, I'll tell you which partial pressures you will need to know later on. But there's oxygen, there's water, there's carbon dioxide, and then there's all the other ones. So that's 100%, which should equal 760 millimeters of mercury. So just make sure you know that as this partial pressure of the atmospheric if this total atmospheric pressure changes, like if you go into altitude, it's going to change all these numbers as well. So we'll look at that later on. So the reason why we want to talk about partial pressure gradients is because of or partial pressures in general, is because of the fact that we're going to be taking a look at two different areas, right? Alveolar gas exchange is going to be looking at how gas is going from the alveoli into the bloodstream. There's going to be a gradient because there's two areas that we're going to look at. So we're going to talk about how oxygen, carbon dioxide separately are going to go down their pressure gradient. They are going to go from a high pressure gradient to a low pressure gradient. Same thing with the systemic gas exchange. We're going to have all these little cells. I'm going to put my nuclei in there to make sure that we know that these are cells and not alveoli. And here's the bloodstream. And again, two different areas. So that is going to create a gradient, and that's going to allow the gases to move from a higher partial pressure to a lower partial pressure. So now first we're going to take a look at this right here, the partial pressure in the alveoli. So we looked at this, and actually it changes just a little bit as we go into the alveoli. It's kind of interesting, right? Maybe not, but it is interesting for me. The fact that the air from the environment goes in and mixes with the remaining air in the anatomic dead space, that's going to change up these numbers right here. Oxygen is going to diffuse out of the alveoli into the blood, and carbon dioxide does the opposite, so that's going to change it right here. And also the fact that there's more water vapor present in the alveoli is also going to change it. If you take a look at water and how much it changed. So that's why you end up with, in the alveoli, you end up with 104 millimeters of mercury for its partial pressure. And you end up with 40 millimeters of mercury for the partial pressure of carbon dioxide. These are the numbers that I want you to know. These are going to be the most relevant ones. So that's in the alveoli. So if we were going in and looking at the alveoli, here's the bloodstream. We care about the 104, that is oxygen, and we care about the 40, that is going to be CO2. That stays relatively constant. Let's take a look at, so PCO2, PO2, and alveoli stays relatively constant. Systemic cells, they are going to stay relatively constant as well. Let's take a look and see what happens in the systemic cells. Look, they are going to reflect what's happening in the cells, which is cellular respiration. So they should be low in oxygen. Look at that, they are very low in oxygen, and they should be higher in carbon dioxide because they're going in and producing more carbon dioxide as a byproduct. So that's good. But if we take a look at what happens with the PO2 and the PCO2 in the blood, they're not as constant. It has to do with this kind of continuous exchange that you have with blood through the lung capillaries, through the systemic capillaries, the fact that oxygen is going to leave the blood and go to the systemic cells and vice versa. You do have a little bit of change. So look, when it leaves the lungs and the bloodstream, the O2 is 104, but by the time it gets here, it's lost a little bit. So carbon dioxide, look, it stays relatively the same. So I know this one says it's not constant, but it stays relatively the same right there. This drops. It's mainly in the pulmonary system where it is going to drop from 104 to 95. So that's what we have here. This is just a reiteration of what we looked at, just in a bigger form. Now let's take a look at our next law before we move on to the whole gas exchange process. Now we have to take a look and see what is happening as far as once gas comes into contact with a liquid. And think about what the liquid is in this instance over here. Blood is the liquid, right? Because this is in the air, and this is going to tissues to be used, we have to talk about what do gases do whenever they are in a liquid. Think about what gases do whenever they are in a soda. That's exactly what they do. They are actually soluble. So gases are soluble in a liquid. But it really has to do with a few things. It has to do with the pressure of the gas in the air, the partial pressure of the gas in the air, and something called the solubility coefficient. So Henry's law states that at a given temperature, the solubility of a gas, meaning how readily does it dissolve in a liquid, it depends on the partial pressure of gas and the solubility coefficient. So let's take a look at the partial pressure of gas. This is the driving force to move a gas into a liquid. So it is determined actually by the total pressure and the percentage. But let's look at total pressure. So here you have a gas and you have a little bit of liquid down here. As you go in and increase the pressure, do you see how you're going in and decreasing the volume? So you're increasing the pressure in here. When you do that, you actually increase solubility. Think about your soda. Think about how they take that Dr. Pepper and they make it fizzy. It's because they go in and put carbon dioxide inside of it and they pressurize it. They put so much pressure in it and they seal it up so the gases are actually trapped inside of the liquid because of this high pressure situation. Now think about what happens when you release that top on your Dr. Pepper or whatever soda you like to drink. Look, this is kind of what's happening whenever you release the cap or the tab off of your soda can or your soda bottle. You are releasing the pressure. You're decreasing the pressure, right? You are going in and opening it, and so the gases can escape. If you leave that soda out for a long period of time, gases are going to keep on escaping the liquid, and your soda is going to be flat. That's exactly what's happening. So just think of your soda as blood and how when oxygen and carbon dioxide come into contact with that blood, it's going to dissolve in that liquid. So that's what's happening there. It also depends on something called the solubility coefficient. This just means how easily does it dissolve. So the volume of gas, let's read it. Volume of gas that dissolves in a specified volume of liquid at a given temperature and pressure. So this is just a constant, and it's going to depend on the interactions between molecules. So carbon more readily dissolves in a liquid. It's more soluble, the most soluble. It's going to have the highest solubility coefficient. The next is going to be oxygen. Look, it's 25 times more soluble than oxygen. And nitrogen is going to be the least soluble of all those. So it means that really if it's not very soluble, you really have to put a lot of pressure into it to try and get it into a solution. So that's what's happening here. Gases with a low solubility, like nitrogen, require a large pressure gradient to push it into liquid. So since nitrogen has a low solubility, it doesn't want to dissolve in blood. So that's why when you go scuba diving or anything like that, it's going in and causing this large pressure, and it does force nitrogen inside of the liquid, which is your blood, and other liquids in the body. The issue is, I think the next thing we talk about is decompression sickness, but the issue with scuba diving is coming up because nitrogen does not want to be dissolved in water. That means that whenever you release the pressure, it is going to escape so quickly because it does not like being dissolved in this blood. So the issue is coming up when you start to release, right? You're not releasing pressure, right? But you are coming up and you're ascending, and that means that there's a pressure decrease. And so when that happens, nitrogen is just going to start to escape from the liquid, and if you come up too fast, it escapes so quickly that all of these nitrogen bubbles are going to get caught in specific places. Not caught, but they collect in different places. So they collect in the joints, and they can collect in parts of the brain and stuff like that. So that's where the issue occurs, is going to be when you are coming up and you're returning too quickly. So that's why they have those little checkpoints. Anytime that you scuba dive, you have to descend, depending on how low you go, really. Or I guess I should say how deep you go, they're going to have these little points to where you need to come up right here at a certain amount of time, and usually have these little, you can wear these little watches that are going to have something that tells you, hey, you're coming up too quickly. So it's really interesting how the whole scuba diving works. But it's called the bends because people, when these nitrogen bubbles get trapped in the joints, it causes people just bend over in pain. But the real term is decompression sickness. So that's usually how they have to treat a person, is with hyperbaric oxygen chambers. It's going in and really increasing the pressure gradient for oxygen, so you can get more oxygen to be dissolved into the blood plasma. And that is going to happen. So during diving, pressure can increase, and that's, so it just said that right there. Nitrogen can dissolve in the blood, significant amounts. So it was just leading up to the decompression sickness. All right, so let's take a look at what's happening. Now that we kind of know what partial pressure is and we know the numbers, let's take a look and see how simple alveolar gas exchange and systemic gas exchange is. So look, here it is in the alveoli, 104 oxygen, PCO2 is 40. Let's take a look at how it's coming in this way. It just dumped out all of the oxygen at the systemic cells. It's coming in deoxygenated. It's never deoxygenated, it's just very low in oxygen. So it's coming in like this. Let's take a look. See how it goes from 104? It goes down the pressure gradient. It goes from a high to a low pressure, partial pressure, 104 to 40. It's going to do this until equilibrium has occurred. 45, carbon dioxide, to 40. It's going to do that until equilibrium has occurred. It's pretty easy peasy. I think it is. So, let's talk about how when it's not so easy peasy, some things that might cause this whole gas exchange to be a problem. Or what are some anatomic features that we really want to make sure that we have to have the most efficient gas exchange we can. We want to make sure that we have a large surface area. So remember, how do we get a large surface area? We've got lots of alveoli, don't we? Yes, we do. We don't have one big giant grape. We've got a bunch of little grapes because that increases our surface area. 70 square meters, that is a little less than half of a tennis court. That's a lot, isn't it? Inside of your lungs, that's a lot. So we want to have plenty of surface area. More surface area means more gas exchange, just more places here that we can exchange gas and get that oxygen and carbon dioxide out. Let's talk about when we might have a problem with surface area. So let's take a look and see what happens when we get rid of some of our alveoli. Nope. I like this little feature here. I can erase it. Look at what we're doing. We're getting rid of some of our alveoli, so we don't have as much gas exchange. So there goes the amount of oxygen that we can get into our bloodstream, and there goes the amount of carbon dioxide we can get out of the bloodstream. So that is not good at all. So this occurs in emphysema, which we'll talk about here in a second. We also want this right here, this respiratory membrane that it's pointing to be as thin as possible. And we do have it. Simple squamous epithelium of an alveoli, simple squamous epithelium of the bloodstream. It should be just fine. Usually it is, but let's talk about when it's not. So what happens when you have it doesn't want me to do that. What happens when you have a layer of fluid sitting inside of your alveoli? So it's kind of like, hey, I want to cross one of these little streets here in downtown Dallas. It's pretty easy. You just push the button, you go whenever you can. But when you add a layer of fluid, it makes it so much harder for oxygen to go through and get to the bloodstream. It's kind of like me trying to cross Stemmons Freeway. It's not going to happen. No, I mean, it will. A little bit of oxygen will go and a little bit of carbon dioxide will go, but really it's not going to be as much as needed. This is what happens in pneumonia, is when you have like this big layer of fluid sitting in your alveoli. So they have to go through the fluid first and to get into the bloodstream. And it just decreases the efficiency. That decreases how much diffusion occurs. So there's less O2, again, less O2 going in the blood, less CO2 going out of the blood. So let's take a look at emphysema. Emphysema, you can see it here. You have some healthy alveoli here with some surface area, but look, this occurs because of smoking is mainly one of the biggest causes is going to be smoking. You get these chemicals and things trapped in the lungs, trapped in the alveoli, and they eventually rupture. And when they rupture, look, there goes your surface area. Another thing that emphysema does is it is going to destroy the elastic connective tissue. So this actually causes an issue with resistance as well, which we talked about last time in the last video. So that's going to be issue. Look, inflammation of the terminal bronchioles, lots of things that we are going to have happening here in emphysema. So that's why individuals with emphysema are going to have issues with blood oxygen and carbon dioxide levels. There is some individuals can have a genetic component to emphysema. If they've never smoked before and they get emphysema, it's because of a genetic disorder, so rarely from this alpha-1 antitrypsin deficiency. So let's take a look at the last thing to make sure that we have a very efficient gas exchange occurring. It's going to be something called ventilation and perfusion coupling. If we are looking at the alveoli and the bloodstream, we want to make sure that airflow is perfect, ventilation is nice, and our airways are open up, and perfusion is adequate as well. What's interesting is it goes through this whole concept of ventilation perfusion coupling, and what that does is going to be where some bronchioles are going to be dilated and some constricted, so they kind of go through these cyclic changes of having dilation and constriction. It's just a little bit more efficient that way. It's able to go in and regulate airflow that way. Same thing with the arterioles. It will go in and have this, arterioles will dilate and then constrict, and so it will just kind of go back and forth as far as, and it's just a way to regulate blood flow. So as long as there's adequate ventilation and perfusion in the various areas, then we have an efficient gas exchange. So I had mentioned this already. Diseases, there are certain diseases like I talked about emphysema, I talked about pneumonia, lung cancer will do it as well, and all of these actually. They cause a decrease in blood O2, blood oxygen, and then that is going to cause an increase in CO2 as well. So congestive heart failure, asthma, really anything that is going to affect ventilation. Remember that we talked about how this affects ventilation with resistance. Anything that affects perfusion, any of these are going to cause issues. It's going to cause a decrease in CO2. It causes an increase it causes a decrease in blood O2. It causes an increase in CO2. So hopefully I got that one right. So let's think about some consequences that can occur. So think about what happens if your kidneys figure out or find, and they'll find out that the blood is low in oxygen. And what it's going to do is it's going to think, oh, there's not enough oxygen? That means there's not enough red blood cells. Let's pump out some more red blood cells for this person that doesn't have enough oxygen. Which, that's not the issue, right? The issue is coming from gas exchange, not from the fact that they don't have enough red blood cells. So some individuals with these disorders and diseases can have a more viscous blood, and that causes issues with the cardiovascular system. And this increase in blood CO2, I don't know why this one has the P and this one doesn't matter. So this issue is it can go in and actually increase respiratory rate, because remember, that's one of the stimuli to increase respiratory rate. It's going to be that way. Let's take a look at the opposite. So we're moving on from alveolar gas exchange. Let's take a look at what happens once we get the oxygen into the bloodstream. We're going to travel it around. That's next, the gas transport, next section. And once we get it to these cells, let's take a look at how we are going to exchange here. So oxygen, all right, so it's coming in, so here it is in a systemic, in the systemic cells. I had to think about things right here. Remember, it's low because of the fact that these tissues are eating up the oxygen, and they are using it for cell respiration and producing CO2. Here we are, we're coming in with 95 millimeters of mercury of oxygen, and we are coming in with PCO2 of 40. So again, it goes down the concentration gradient. It goes from this 95 to 40 until equilibrium has been reached. And same thing here. It goes from that 45 to 40 until equilibrium has been reached. So that is what's going to happen. All right, so that's it for gas exchange. Our next thing that we are going to do is take a look at gas transport. So until next time.